Welcome to part 2 of session 15 on thin-walled pressure vessels. This portion of our session is going to focus on some examples that you might encounter that use the equations that we've derived for the hoop stress and the longitudinal stress in a cylindrical pressure vessel and the stress or kind of the equivalent of the longitudinal stress in a spherical pressure vessel. So let's go ahead and start with the following problem. We have a cylindrical pressure vessel, has internal radius of 10 centimeters with an internal pressure P. This is a gauge pressure of 10 atmospheres. So we're saying that's the difference between the pressure inside the vessel and the pressure surrounding it. Has a thickness of 5 millimeters. And we're asking what are the sigma x and the sigma y shown in this diagram. Well, sigma x is going to be in a circumferential direction, around the cylinder. And that is what we would consider to be a hoop stress. And we can write that out as sigma x is equal to PR over T. And when we do the calculation, we plug in the parameters, and it's fine to write things out like I've written them. Just we need to be aware that the units are not going to cancel naturally. We have to do an additional step, but I've skipped that. And the answer is 20.3 megapascals. For the stress in the y direction, so this one that we see, and we're asking for sigma y, that's going to be in the longitudinal direction. So that has the form of sigma y equals PR over 2t. And we could redo the calculations, or we could just say, well, that's going to be half of what we calculated for the hoop stress. And so that comes out to be 10 megapascals approximately. Okay, so that's kind of one of the most basic examples of there's the formula. We know what the internal pressure is. We know what the radius of the pressure vessel is. We know it's cylindrical, and we know its thickness, and we can calculate out the hoop stress or the circumferential stress along with the longitudinal stress. Let's do another example. This one has us looking at a slightly more complicated problem, but it's with a spherical pressure vessel. And we're going to be interested in the strain, all right? So we're given some internal radius, and we're given some internal pressure and thickness, and elastic modulus, and Poisson's ratio, okay? And the question is, what are this epsilon x, epsilon y, and epsilon z? Well, first we need to think about, okay, and you need, I need to define things a little bit here, right? So here is a really poorly drawn spherical pressure vessel. That's a ball. It's a hollow ball. And what we're saying is, okay, let's pick an element on the surface or kind of just inside the shell of the spherical pressure vessel. And let's say that we're going to call this direction x, we're going to call this direction y, and then z is going to be coming out of the page. So, we know how to calculate sigma x, we know how to calculate sigma y, and we know that sigma z is 0. We discussed that in the last portion. And Professor Roylance gives a nice succinct explanation for why that might be. But just because we have a 0 stress in the z direction does not mean that the stress or the strain is going to be 0. Okay, so, well, foreshadowing like 30 seconds in advance. Okay, so here are the parameters. We can list them out. We know how to calculate sigma x and sigma y. In this case, they're equal to each other, right? Because we have the equivalent of what would be a longitudinal stress in the spherical pressure vessel, or would be equivalent of longitudinal in a cylindrical pressure vessel. So anyway, it's PR over 2T, and wow, that number looks vaguely familiar. Well, it is. It's because we just did it in the last problem, example 15.1. And we can also write out that the stress in the z direction is equal to 0. So if we go back a ways, I'm not quite sure which session number it was, but I think it was the one material properties 2. Okay, is what we called it. We can write out this relationship between the stresses that we might have and the strains. Okay. And what is new here? New is the Poisson ratio, right? We talked about how, hey, if you are applying stress in an orthogonal direction, that's going to lead to some contraction in another direction. Okay. Or if you're applying some, so like, if we apply a positive stress in the y or the z, it's going to cause there to be some contraction or some compressive strain in the x. So if you want, you can take a refresher, look at those equations, go back to the material properties sessions. But here, what we can do is plug in, the elastic modulus, the sigma x, sigma y, and sigma z is equal to 0. And we get that epsilon x is going to be 35 or 36 microstrain. And guess what? Epsilon y is going to be the same. Okay, well, sigma x and sigma y are the same. Sigma z is still equal to 0. So we can once again write down this strain. Now, there's no sigma z, or it's 0, okay, in this direction kind of coming out of the shell. It's a radial direction. So that automatically means that the strains that we're interested in are going to be dependent on the stresses that we do have, okay, sigma x and sigma y. And it means that the strain in the z direction is going to be negative. That's meaning that the thickness is actually getting slightly smaller. So when we do that calculation, this is what we find. So that's pretty much all you have to do. For kicks, if you want to recall the matrix form of being able to calculate epsilon x, epsilon y, epsilon z, and these are column vectors, here's a matrix, then we can do the same thing that we just did and write the result, but now it's in the form of a column vector. Okay, great. So that's example 15.2. It gives us an idea of how to relate the state of stress to the state of strain in the structure and the material of these pressure vessels. Let's do another one. Here we have example 15.3. And this one is a little bit more complicated. And we're going to kind of do it two ways. It's pretty much nothing changes about kind of the methodology. It's not like we're using internal equilibrium for beam bending, and then we're using the integral and differential forms of dv dx equals w and dmvx equals v. No, this is the same way, just kind of showing a couple different ways to do the algebra, essentially. What we have is a bladder, okay, and a ring that's placed around it. Okay, so this ring is metallic. It has a significant elastic modulus, E. And this bladder, it's kind of rubbery. It just kind of goes along, for the purposes of our assumptions here, it just goes along for the ride. Okay, is this completely realistic? Maybe, maybe not. Okay, because the bladder, depending on its strength and how much pressure you put in it, right, it could burst. But we're saying, okay, don't worry about those things. It's just a nice, flexible, rubbery bladder that goes along and perfectly conforms to the ring. We have some parameters. We have the inner radius, Ri, and this is describing the ring. Okay, we have outer radius, R0, again, for the ring. And the bladder's right inside up to it. We have internal pressure, P, that's the pressure inside the bladder. We have elastic modulus, E, for the ring. And my drawing's not the best, but you can kind of see that it is going around. And this is problem 814 in Hibbler's, I believe, 9th edition. And it's also treated in Roy Lance's engineering libre text. So it's I guess it's kind of one of these somewhat standard problems. We have this this question here facing us is how do we calculate the change in the radius? Well, first we're going to define a bunch of parameters and think about how the change in radius is related to the change in the circumference, okay, of this ring, okay, around the bladder. So here we go. First, maybe it's more convenient to think in terms of a thickness for this ring, okay, and so we'll say that's R naught minus or R outer minus R inner, however you want to look at it. And you've seen this drawing before. We're just saying, look, we take the ring, or if it were a cylindrical pressure vessel, and we can think about which stress. This is the hoop stress. Okay, it's going around, okay, and there's an internal pressure inside, and that pressure is transferred perfectly from the bladder to the inside of this ring. We have sigma 1 as our hoop stress, and we can write that, well, it's going to be PRI over T. And something that I probably didn't emphasize too much is that we typically think of using the internal radii when we're looking at these calculations of stress, of hoop stress or longitudinal stress. It often doesn't really make that much of a difference in terms of kind of, if you think about, okay, the projected force, even if there's some strain, it's small, or even if there's there's a difference, of course, between the inner and the outer radius. It doesn't make a whole lot of difference, especially since we're saying that thickness is like 1/10 or less of the radius. But anyway, we're going to use the internal radius, and that makes it a little easier to do some of the accounting that we're going to do in the next few steps. So sometimes, like Jeff Hansen and others, they'll say, okay, I'm going to use this circumference variable c. Let's just use Li here. I can't even remember if that's what Hibbler uses or not, to be honest. Okay, but Li is the circumference, and it goes around the essentially the whole ring. Okay, and it's 2 pi Ri, right? And so now we're starting to see, okay, we're being a little bit careful. That's Ri, that's Ri. This is Li. So how does the circumference change? Well, we can say that it's going to change with the change in the radius, right? So 2 pi r. So if there's a 2 pi delta Ri, as we see here, there's going to be a change in their circumference of delta L. Now we're talking about a length, right? It goes around, it wraps around the ring, but this is, I can unstretch it and I have a length, and we can think of what is the normal strain, okay, along that length, or how much is that going to change if I know the strain and an initial length, okay? So that can be given by epsilon 1. Now, we don't yet know what epsilon 1 is, but right, initial length times the strain gives us a change in length. Or you could look at it as the change in length divided by the initial length is equal to epsilon 1. Let's go ahead and combine these two equations with each other. And we have 2 pi delta Ri from over here is equal to epsilon 1 Li. And epsilon is here, sigma is here. And we have an elastic modulus. So what do? We pull out Hooke's law, and we say sigma 1 is equal to E epsilon 1. Okay? And then we can combine these terms, right? This Hooke's law and the hoop stress to say that epsilon 1 is going to be PRI over ET. I think you can see where we're going now, right? Now we have epsilon 1, we have epsilon 1, and we can then do that substitution. Also keep in mind that Li is the circumference up here. So that's the 2 pi r I right here. Okay, so that's this term. Epsilon 1 is this term, and then this left term stays unchanged. We were interested originally in the change in radius. Okay, what is the change in the internal radius Ri? And so we have 2 pi times the change in internal radius equal to this expression, 2 pi, this Ri times Ri becomes Ri squared, and we get the following result. So not too difficult to follow if you keep track of all the steps, but maybe a little bit tricky to do if you haven't seen the problem before. Okay, which is maybe that's an obvious statement, but that's often the case with these. Let's do this problem a slightly different way. It's like just saves us maybe 1 or 2 lines. Okay, and this is how Roylance thinks about the problem. And you can take a look here at the Engineering Libre text. Roylance says, I'm going to define an epsilon theta, all right? And that is essentially, I mean, that's kind of what we just described as epsilon 1, okay? So slightly different term, but maybe a little bit more descriptive because epsilon theta is now the circumferential, and it's very clear what that is. Then immediately jumps into Hooke's law. Okay, so that's equal to sigma epsilon, right? Which is what we were calling sigma 1, right? So maybe not the best way to mix and match parameters, but sigma 1 and sigma epsilon, sigma theta are the same. This is Hooke's law right here. And then we have the hoop stress, okay? And so immediately we're now into PRI over ET, okay, because the E is there, that's elastic modulus. And we can also write that the strain, okay, and we kind of wrote this before, but the circumferential strain, right, can be thought of as a change in length, okay, over the circumference, okay? So what is the change in length over the initial circumference? That's epsilon theta. You see where this is going. We're going to set these two equal to each other. And so what do we get? We get that delta L, okay, equals this quantity times epsilon theta. And we have an expression for epsilon theta up here, okay, that's PRI over ET. So we write that there, okay, 2 pi r PRI over ET. And we can say that the change in length, okay, is going to be 2 pi Ri, okay, times this epsilon theta. Well, actually, we already wrote that, okay. So we can simplify down a little bit, okay. So we have delta L, and we have a 2 pi delta Ri, and when we go to this step, all right, we now are able to say, well, delta Ri is equal to delta L over 2 pi, and delta L is equal to this expression that we have here, okay, and that's the result that we have. All right, actually, so I guess I kind of fumbled that a little bit, but I don't want to go back and re-record. This expression, right, is very similar to the expression that we had just from geometry at the very beginning, right? Saying that if you have 2 pi r, right, that's equal to L. So if I have a 2 pi delta Ri, that's equal to delta L. Okay, thank you for your patience. So that concludes the instructional portion. I just want to review the questions that are now posed on the website and for the class. Here we have a cylindrical pressure vessel that has internal radius r, internal pressure P, thickness T, elastic modulus E, and Poisson's ratio nu. And it's asking for what is the strain in the x direction shown in this diagram. And this is very similar to what we did with a spherical pressure vessel, but now we're doing it on a cylindrical one. When I say what we did when we were looking at using the relationship, the material property relationship, right, accounting for the Poisson's ratio. Question 3, all right, is I think kind of a fun one, but but maybe you won't. All right, think it's that fun. But what we're saying is we have a fuselage for an airplane, and that's something you can kind of approximate as a cylindrical pressure vessel. And when the airplane goes up in the air, okay, it actually doesn't keep the internal cabin pressure exactly. It actually it drops it a little bit, okay, because it turns out that you have to have a thicker shell, right, if you have a higher pressure differential. But in this case, we're going to say, let's assume that the internal pressure is at sea level, and the surrounding pressure can be calculated up in the air as a function of altitude, okay? This little h right here. So now we have internal pressure. This is kind of an absolute internal pressure at sea level, which is 101.3 kilopascals. And depending on what the height is, we have some absolute pressure outside. We can figure out what the gauge pressure is between the pressure inside and the pressure outside, and that becomes the P that we're going to use for our calculations of hoop stress or longitudinal stress. Okay, so this gives you an idea of how much pressure or how much. Yes, well, it gives you an idea of how much change in pressure there is, gauge pressure, the cabin versus the outside there is. And it also gives an idea of how much stress would be in the shell, okay, in the hoop direction and in the longitudinal direction. And of course, the longitudinal direction is going to be half of the hoop stress, okay? And later we'll see how it's still, you're like, oh, but I just take the bigger one and I'm done. Well, we're going to talk about transformations in a little bit and being able to kind of account for these different stresses. Okay, both the hoop and the longitudinal. All right, so that's question 3. And then question 4, this one's a little bit tricky, all right? But we have a compound cylinder with an inner cylinder. So compound cylinder essentially means cylinder inside a cylinder, okay? So the internal one's hollow, and then we have an outer cylinder that fits snugly, okay, around the inner one. And, oh, I didn't change these properties here, okay? But it'll show appropriately on the website that the outer cylinder, the radius, the internal radius, okay, is going to be defined. So this R2 is really just R1 plus T1. Okay, so we have R1 is the inner radius of the first inner cylinder. When we go out a T1, and that becomes what R2 is. All right, and then there's another thickness for the outer cylinder. The question is, what is the hoop stress in the outer cylinder? And this is an interesting problem. We kind of talked about things a little bit with how when we had the ring around the flexible bladder, we kind of treated this a little bit in terms of just what would happen with one ring. But now we have a ring inside of a ring. And so there needs to be some accounting of geometric compatibility, right? These two are going to have an expanding radius that matches each other, okay? And there's going to be some capturing of the pressure in the initial one, right? So the pressure that the other one experiences is going to be different on the outer one. So to get a great description actually from this, take a look at Roylance's page. That does a very nice example, 2.2.2, and will allow you to solve this problem. Okay, so that concludes session or part 2 or portion 2 of session 15 on thin-walled pressure vessels. Thank you.